Soft drinks contain 11. Soft drinks contain a variety of sugars. A student investigated the sugar content of a soft drink. The density of the soft drink can be used to estimate its total sugar concentration. Solutions of different sugars with the same concentration have similar densities. The first experiment was to determine the total sugar concentration of the soft drink by comparing the density of the drink with the density of standard sucrose solutions. Okay. This first involved producing standard sucrose solutions of different concentrations. The standard sucrose solutions were made up in volumetric flasks. Draw a diagram of a volumetric flask. It's a really odd question, but that's what they gave you. So what you need to draw for a volumetric flask is you need to have, so dodgy to draw on the little graphics thing, you need to have a long narrow neck, and then you need to have the kind of rounded base. Oh, you're going to draw that so much better than me. And what you must show is that we have a single graduation mark. I personally, because my diagram's so dodgy, would have said there's the graduation mark, just so you could say it was there. And if you wanted to do a wee stopper in there, that would be fine, but they just asked you for the flask. Okay. The density of each standard sucrose solution was then determined. In order to determine the density of each solution, the student accurately measured the mass of 10 centimetres cubed of each sucrose solution. Describe fully a method that the student could have used to accurately measure the mass of 10 centimetres cubed of each sucrose solution. Okay, so there's two parts to this because there's two marks. So first of all, I need exactly 10.0 centimetres cubed. And then I need to find a way of the mass of that. So I have a volume measurement and a mass. So my volume is going to be quite easy. Okay, I'm going to use a pipette. Oh, don't even know what that word looks like. Let me write that a little bit clearer. Okay, you're going to use a pipette, not super clearer, but you know, it's better. Use a pipette to accurately measure 10 centimetres cubed. Okay. And then we're going to have to measure the mass of that. So to measure the mass, what I'm going to do is use a beaker on top hand balance. That has been, you can either say zeroed or tare. Okay, so what you've done there is you take the beaker, tare it, so you put it to 0, and then you add in your exact 10 centimetres cubed, and it will give you exactly the measure of what that was. Or you could do mass by difference. So what that means is you put your beaker on top, you note the mass, you add in your 10 centimetres cubed, you note your mass, and then you take them both away and you'll get how much the 10 centimetres cubed weighed. Either is good. There's your first mark and there's your second. Okay. The results that the student obtained for the density of the standard solutions of sucrose are shown. There we go. Unusually, we don't have too many of these, but draw a line graph basically using the student's result. Additional graph paper can be found on page 38. Right, so this is just plotting it. Now I'm not going to plot this in. I'll try actually. Okay, so I've got 0 and 1 here. 5 is 1.1. I think that's there. 10, 1.19. These are going up. That's the 10. This is going up in 0.1, so pretty nice scale actually. 15.31, 0.31, and 20 is 0.41. Okay, so this is going to give us a very nice straight line, which you're going to connect up. Okay, and that's your 2 points, one for the plot and one for the join. They allow you half box tolerance. So that means that if your line is within half a box of where it should be, then it's okay. But those are bang on cross points, so there's no reason to get that wrong. Student used the line graph. I wonder if I can shift this to the side actually. I mean, it's a little bit bigger. Okay. Student used the line graph to obtain the relationship between the concentration of sugars in solution and the density. Equation shows the relationship. So basically they've solved it as a straight line. The student then determined the density of soft drink in order to ensure that the drink was flat. All the gas had been allowed to escape. suggests a reason why the soft drink needed to be flat before its density was determined. So it's basically that we have volume taken up by gas. So that means that you've not got a true measure of the exact volume of the liquid, and it's a liquid that we need. Okay. Use the equation, calculate the percentage concentration of sugars present in the soft drink they tested had a density of 1.07 grams per centimetre cubed. Okay, so I need to rearrange my equation, this one up here, for percentage concentration. So percentage concentration is going to be the density minus 1 over 0.0204. Okay, we're happy with that rearrange of the equation. And then you just plug in the numbers. So 1.07 as my density, minus 1 over 0.0204. Plug it all into my calculator, gives me 3.43%. That's it. I moved that to the side because I thought there was something to do with the graph in there, but there isn't. A different soft drink is found to contain 10.6 grams of sugar in this 100 centimetres cubed. Calculate the total mass of sugar in grams in 330 centimetres cubed can of this drink. Okay, a straight proportion thing. So 100 centimetres cubed had 10.6 grams. 330 centimetres cubed. Oh, 330, sorry, centimetres cubed. Therefore, so 330 divided by 100 times by 10.6, 34.98 grams. Pretty straightforward. Okay. Second experiment, spin it down a bit. Second experiment in this investigation was to determine the concentration of specific types of sugar called reducing sugars. This was carried out by titration with Fellings. Reducing sugars contain an aldehyde functional group. Draw this functional group. C, double bond O, bond H. Okay. The overall reaction that occurs with Fellings solution and a reducing sugar is shown. Write the ion electron equation for the oxidation reaction. Okay, so we've got a redox going on here. So oxidation is loss. Okay. So the one that is obvious here is the copper, and the copper has gone from 2 plus to 1 plus. So that has actually gained an electron, so it's the reduction. So it's not the copper. I am actually looking at this. So what I'm looking at is C6H12O6 going to C6H12O7. Now you could pull out the water and the hydrogen ions from that. I'm going to work the full thing just as if it was one of those ones where they say do the complex equation, because I think that shows it a bit better. Okay, so the first thing you do is you always balance your oxygens with water. So I've got 6 oxygens on this side, 7 on that side, which is why I've got a water in here. Okay, and then I balance my hydrogens with hydrogen ions. So on this side I now have 14, and on the right side I have 12, which is why I need to put this in. Okay, and then I finally balance my charge with electrons. So this side has no charge, this side has +2. So to get that down to nothing, I'm going to have to put in 2 electrons. Okay, and it was the oxidation. Oxidation is loss, and that is right. Okay, I'm happy with that. Okay, state the colour change that would be observed when reducing sugars are reacting with Fellings. You just have to memorise all these ones. It starts blue, all your copper ones do, and it goes orange. Or you might have gone with brick red, especially if you can associate that with Benedict's from earlier in your courses. Oh, don't need that bit, this way. Right, for the titrations, the student diluted the soft drink to improve the accuracy. 25 centimetre cube samples of the diluted soft drink were titrated with Fellings and had a copper 2 plus concentration of 0.025 more. The average volume of Fellings solutions used in the titration was 19.8. Calculate the concentration in moles per litre of reducing sugars present in the diluted sample of the soft drink. Okay, you have 2 ways of doing this. I will run them both. Okay. V1 maybe is the shortcut. Okay, shortcut method would be to use C1 V1 over N1, C2 V2 over N2. Okay, so the N1, N2, remember, are the moles in the equation. So in this case, we've got 1 to 2. Okay, this is not the moles that you get in terms of the moles that are there. So we are trying to calculate the concentration of the sugars. Okay, so we're going to make that C1, or the ones. So that's going to be C1. Volume of the sugar sample was 25 centimetres cubed. Okay, divided by the moles in the equation, it's 1. And then on the other side, we're going to take our copper. So the concentration of that one was 0.025. Going to times that by the volume, 19.8, and divide that by 2. Okay, which means that we are looking at, for C1, we are looking at 0.2475, which is all of this bit, divided by 25, so 0.0099 moles per litre. Okay, shortcut method. Really happy to use it as long as you know exactly what you're doing with it and you do not mess up with these. Okay, that you don't try and calculate moles and stick that in. What you must do as well is recognise that it is okay in this one, but only in this one really, to convert, or not convert rather, but as long as you still have them in the same volume. So they're in centimetres cubed, I can keep it like that. Okay, if we were using the normal standard method of how you work any kind of mole calculation, start with your A, B, C1. So A, find out anything that you can, find any moles. And the only one that you can calculate is copper. Okay, because copper we have as moles is concentration times volume. Okay, concentration 0.025 times my volume 0.0198. Okay, this time I'm converting it into litres. Means the moles of copper 0.000495. Okay, B, go from a balance. So that is copper to my sugar is a 2 to 1. So I'm going to divide it by 2. Divide this by 2. Means that I've then got my moles of sugar at 0.000247.5. And C, do my final calculation. So this time, I'm looking for my concentration of my sugar is moles over volume. Okay, so this one, 0.002475 divided by volume at 0.025 gives me 0.0099 moles per litre. Okay, exactly the same answer, just running it different ways. Okay, effectively what you're doing with all of those ratios, okay, so the ratio for B is actually being done here, and then you're just doing this calculation up here, and then you're doing the final calculation here, down here. Okay, so you're doing exactly the same thing, but whichever works best in your head. Okay,